Alright, hi everybody. In this video we are doing section 8.1 from your textbook. And all of chapter 8 is dealing with what we call sampling distributions, where 8.1 is going to be discussing the distribution of the sample mean. And 8.2 is going to be discussing the distribution of the sample proportion. And maybe that doesn't mean a whole lot to you yet, but that's what we're talking about today. Let's first consider this example. Suppose there's 5,000 Midland College students, and what I have is some made-up data, that's in a spreadsheet. And what we're going to do is we're going to randomly sample 30 of them. We're going to take their height in inches, and we're going to calculate the sample mean of those 30 students' height. And here on the page, what you can see, that red curve is a normal probability density function curve. So that's the normal PDF curve, which is that classic bell shape. And it has a mean of 67 and a standard deviation of about, it looks like 3 or 4. So anyways, maybe this is the probability distribution. 67 inches seems like maybe an average height of a college student. And so maybe this is a reasonable distribution here in red. That one might describe what we're talking about. But here in my spreadsheet, let me zoom in for you. In column A, I just have, suppose I measured the height of all 5,000 Midland College students. I didn't, by the way, but, imagine I did, and I came up with all of these numbers, like I said, that are centered around 67, but have some variance from one student to the next, because, not all students have the same height. Now, what if I just randomly sample 30 of these? Well, to get 30 students sampled, I'm going to have to generate 30 random numbers between 1 and 5,000. All right, so let me just drag this down, generate 30 random numbers. And these are now going to be the indexes for 30 students that I'm going to pick out. So I have to add some index to my list, and I'll just number these measurements 1 through 5,000. And now that that's done, just to show you, I've got 5,000 of these measurements in the list here in column B. And then what I'll do here in column E to get the measurement of 2,128, rather than spending the time scrolling down and finding that one by hand, I can use the formula Vlookup in Excel. And the lookup value is going to be that one, 2128. The table is going to be the range of cells between A1 and B5000. The column index, where I want to draw my data from, is column B, so that's the second column in that range, and that's the formula we need. By the way, I'm going to put little dollar signs in front of the A and the 1 and the B and the 5,000, because as I drag this formula down, I don't want that reference range here in shaded red to move on me. Okay, so clicking enter and then dragging down the bottom right corner of that cell so that I can apply that to all of these. Now, here in column E, I've looked up the height of the students with these indices. In column D, remember, these indices were just random numbers. So I've randomly selected 30 students and found their height, is the idea. And then to take the sample mean of this random sample of students, type in equals average. And then I want to average column E, which is just the sample of 30 students. So my sample mean here is 66.2 inches. And this is the idea of what we're doing here. By the way, just out of curiosity, let me find the population mean of Midland College students. And this would be taking the average of column B here where I have the height of every single student. So my population mean is 66.96 or 67 inches, whereas my sample mean is 66.2 inches. So this makes sense because the sample mean is a descriptive statistic. And what that means is the sample mean is an estimate of a parameter. Remember, a statistic is just an estimate of a parameter. Our population mean, that's the parameter. That is the characteristic of the population, that population's mean height is 67 inches. But the sample mean is just the statistic that gives a good estimate of the population using what measurements we have in a particular sample, right? So it got close. The sample mean's close to the population mean, but the sample mean will never exactly be the population mean. And that's important to understand for this chapter here, is that our descriptive statistics will never exactly match our parameters. They're going to try to estimate the parameter as well as we can, but there's going to be some error introduced. In other words, depending on what sample you take, you'll get a different sample mean. So if we take a bunch of samples, none of them will agree. There's going to be a little bit of variance in between sample means if we take multiple sample means. Okay, so this is what we've done, steps 1 through 4 here. Now, step 5 asks me to repeat steps 3 and 4 5,000 times. So I need to randomly sample 30 students and then calculate the sample mean and do that 5,000 times. So I'll have 5,000 different samples of 30 students. I'll be calculating 5,000 different sample means. So to do this, I've pre-prepared a little program. I'm going to reset my spreadsheet so my height measurements are in column A, and of course there's 5,000 measurements there. But what my little program does is it's going to automatically do what we just did. It's going to randomly select 30 numbers between 1 and 5,000. Then it's going to pick out the measurement with that particular index. It's going to add up 30 of those randomly selected measurements, and then it will divide by 30 to get our sample mean. Whenever it does that, it's going to deposit the sample mean here in column B, and it will repeat that process for me 5,000 times. So as soon as I press the button, column B is going to be populated with 5,000 sample means, where each sample mean is the mean of 30 randomly selected student heights. So let's try that now. Oh, I said column B, but I guess I meant column C. So anyways, column C, again, each entry in column C is a sample mean. Each entry in column A is the height of a student. So let's just quickly see, by clicking on column A, going to insert, and we want to insert a histogram. We can see that column A, the data in it is normally distributed, right? So of course, this is random. This is a random process, and so whenever you generate a histogram with empirical data, it's not going to follow a perfect bell curve. Like you see, there's some blemishes in our bell curve here, but it's still visibly recognizable as a bell curve. Let's now look at column C and see what that distribution is of these sample means. We know these sample means are randomly distributed because they're not all the same, but what is the distribution of the sample means? Look at that. In fact, it's an even nicer bell curve. It looks even more true to form, this bell curve we get from this histogram of sample means. Now the difference between this bell curve and the bell curve for the raw measurements is that actually the dispersion of this data is a lot less. So you could say the variance is a lot less, or the standard deviation is a lot smaller, because if you look at these buckets, and I apologize because it's sideways here, you'd have to pause the video and turn your head left 90 degrees. But looking at these buckets, they're very thin buckets. And the bottom one starts at about 65 inches, and the top one ends at about 69 inches. So this whole distribution of sample means is contained between 65 and 69. Whereas these heights have a histogram where the lowest bucket starts at about 56, and the largest bucket, or the highest value, ends at like 78. And so there's more dispersion in the raw data than there is in the sample means. And what this means for us, I think I have a good visual of what's going on here, is whenever we have the distribution of the sample mean, like this one in blue, the standard deviation is smaller, and so the probability density for the sampling mean distribution is actually going to be more tightly bound up around the mean. Notice, though, that the mean of the blue distribution and the mean of the red distribution are actually the same. So the mean of your sampling distribution is the mean of the underlying process. And visually, you can see that the red curve and the blue curve are centered around the same point at 67 inches. But just the blue curve does not have as much dispersion because the blue curve again represents the distribution of sample means. The red curve represents the distribution of the raw data. Now here are some important rules to notice. If the underlying distribution of individuals is normal, in other words, it follows a normal probability distribution, then the distribution of the sample mean will also be normal. On the other hand, if the underlying distribution of the individual measurements is non-normal, because there's other probability distributions that it may follow, then the distribution of the sample mean could still be normal if your sample size is greater than or equal to 30. So that's interesting. If your sample size is less than 30, then your sample mean won't necessarily follow a normal distribution. But if you have a sample size greater than 30, then regardless of the underlying distribution of individual measurements, your distribution of sample means could still be normally distributed. And this is one of those really convincing points. You know, when we say that the normal distribution appears a lot in nature, maybe that's because a lot of natural processes have a built-in averaging to them, right? So whenever you see that happening, you tend to have random processes that follow a normal probability distribution. And we're going to see some examples of this as well, so you don't have to take my word for it. You'll be able to see some empirical evidence. But here's the parameters that describe the distribution of the sample mean. So the mean of the sample mean, which I'll denote with a mu with subscript x bar. Remember, x bar means the sample mean. And when we have the x bar in the subscript, it's talking about the mean of the sample mean. So mu with subscript x bar is equal to mu. So that just means the sample mean has the same mu value, or the same mean, as the distribution for the raw individual measurements. So that's nice and easy. What about the second line where it says sigma subscript x bar? Well, that's the standard deviation of the distribution of the sample mean. That's equal to the standard deviation of the underlying process, so the standard deviation of the distribution of the raw individual measurements, divided by the square root of the sample size. So remember, lowercase n refers to the sample size. And so the effect of our sample size on the distribution is that whenever the sample size grows larger and larger, the standard deviation of the distribution of the sample mean is going to get smaller. Think about that, because when n gets larger, square root of n gets larger as well. The square root of a larger number is, well, it's a larger square root. And whenever the denominator of a fraction becomes larger, the value of the fraction itself becomes smaller, right? So like 5 is greater than 4, but 1/5 is less than 1/4. So in this case, if n becomes larger, then the standard deviation of this distribution of the sample mean will become smaller. These are important formulas to know, that's why I put them in a green box. But again, on an exam, you'll have a formula chart that will include these formulas for you in case you happen to forget them. But they will be very important to use here. So here's example problem number 1. It says intelligence quotient, or IQ, is normally distributed with mean 100 and standard deviation 15. Suppose you randomly select 10 individuals and test their IQ. Our first question says, what is the distribution of the sample mean? And the answer comes from a previous slide. So this slide says, if the underlying distribution of the raw individual measurements is a normal distribution, then the distribution of the sample mean is normal. So since I told you that the distribution of the raw individual measurements is normally distributed, so intelligence quotient is normally distributed among the individuals in the population, that means the distribution of the sample mean must also be a normal distribution. What would be the distribution if you select 20 individuals? Well, it would also be normal. And what if you selected 40 individuals? Again, normal. Let's calculate mean and standard deviation of these three cases. So in this case, the mean, or the mu with subscript x bar, the mean of the distribution of sample means, that's going to be the same as the mean of the underlying distribution. In fact, that's the case for all of these cases. The mu subscript x bar is going to be equal to 100 because that's the mean of the underlying distribution. Okay, well, what about the standard deviation of the distribution of our sample mean? Well, this is sigma over square root n. So this is going to be 15 over square root 10. And if you have a calculator, you could, of course, figure out what that is exactly. In fact, maybe we'll do this, and maybe my sigma looks more like a 6, and so I want to correct that just a little bit. Let me make a better looking sigma. There we go. There we go. And I'm going to pull up a calculator so we can actually figure out what is 15 divided by square root 10. Well, square root 10 is just a little bit more than square root of 9, so it's just a little bit more than 3. And 15 divided by 3 would be 5. So this is a little bit less than 5, I think. Sure enough, we're a little bit less than 5 at about 4.74. So this standard deviation of the sampling distribution is going to be 4.74. Okay, what if we select 20 individuals? Then this now becomes 15 divided by square root 20. Let's see how that affects things. So now 15 divided by square root 20 gives me 3.35. Notice as my sample size increases from 10 to 20, my standard deviation has decreased from 4.7 to 3.4. And then finally, what if I have 40 individuals? Well, you probably can see what's going to happen. Increasing the sample size means decreasing the dispersion of the sample mean. In other words, you can think the sample mean becomes more accurate, or the sample mean becomes a better estimate of your population mean if your sample size is larger. So this is 2.37 in this case. 15 divided by root 40, and this is, I already forgot it, it was like 2.37. So again, notice the decreasing trend and standard deviation of this distribution of the sample mean. Whenever I use a larger and larger sample size, that means that this descriptive statistic is getting more accurate with a larger sample size, and that's always true about descriptive statistics. It's always nice to have a larger sample size. It means you can make better guesses or better predictions about your population characteristics. Here's example 2. This says, in a football punting contest among Midland College students, the punt distance in yards is exponentially distributed with mean 20 and sigma 20. You randomly select 10 individuals and you measure their punt distance. So don't focus too much on where it says exponentially distributed. I don't want you to be familiar with the exponential distribution. Just know that this is some other probability distribution. That's not terribly important, but the point of me indicating this is that it's just non-normal. It's not the normal distribution. It's some other distribution. That's the important part. So what is the distribution of the sample mean? Well, notice we only selected 10 individuals, and so that would mean that this sample mean follows a non-normal distribution. The underlying process wasn't normal, and I didn't select a large enough sample size to make that normal. But if we randomly select 30 individuals, then let me remind you of what we said on the previous slide. If the underlying distribution is non-normal, then the distribution of the sample mean is still normal, provided that your sample size is greater than or equal to 30. So here, in the second bullet point, this is actually following a normal distribution, despite the fact that the underlying distribution was not normal. Now let me actually demonstrate this to you using Microsoft Excel. This should be relatively straightforward to simulate. We'll open up a new page, and in column A, I'm just going to generate some data. So we want the exponential distribution, and give me one moment while I look that up. Okay, so I just had to look up really quick, because I don't do this a whole lot, what the formula is to generate data that randomly follows a exponential probability distribution, and so this is the formula that I've applied. And just to double check, I tried to put in a population mean and a population standard deviation of 20, and so we can check this with Excel, because my descriptive statistics of sample mean and sample standard deviation, those should match pretty closely to what I need as the population mean. So here's my sample mean, and it's pretty close to 20. And let's see if the sample standard deviation is pretty close to 20 as well. 19, 18, 21, a little bit higher, a little bit lower, a little bit higher. So yeah, they seem to be centered around 20. I'm going to freeze these in place now. So those values aren't going to change. So imagine this is the distance, again, in this punting contest among Midland College students. So they're at the football field, they're having fun punting around footballs. Let's insert a histogram so you can quickly see what an exponential distribution looks like. And what this means is a lot of students aren't punting the football very far, right? You have a lot that fall into this first category of barely getting the football off their foot. And you just have very few students who are really great at punting the football and can punt like 90 yards, for example, right? That's a pretty good punt for a college student. So you would have this sort of distribution rather than a normal distribution in this kind of situation. Well, my next question was, what if I sampled 10 students at random? What would be the distribution of the sample mean? So I'm going to use my fancy program that works behind the scenes, and it's automatically going to select for me samples of 10 students at random, and then it's going to take the sample mean just like we did before. And so now in column C, I have sample means generated from randomly selecting 10 students from this group and calculating sample mean. So let me put in a histogram that describes this distribution. And I want to point out to you that this looks more bell curve-ish than the raw data, for sure. But I would still say that this is right skewed because this right tail is quite a bit longer and fatter than the left tail of the distribution. And a normal distribution is symmetric. It's not right skewed or left skewed. So this is clearly not following a normal distribution yet because of this heavy right tail, because the distribution appears right skewed here. So let's try this again. And this time I'm going to tweak my program to tell it to pick up a sample size of 30 students before calculating the sample mean. And I'll clear out this column. We're keeping the same raw data. Running the program again, and this time when I insert a histogram, well, it looks a little bit more normal. Maybe it's not perfect yet. Maybe we should try to rerun the program a few times and maybe it'll get better, right? Because each time I run this, it's making random selections of the sample, so it's going to change just a little bit each time I run. Not every sample is going to be the same. So it's still not perfect yet. Maybe you see that the right tail is a little bit heavier, but it's getting better. It's becoming more symmetric. What if I increase the sample size, heck, to a lot more, like 100? We're going to include 100 students in our sample size. That's significantly more. So I would actually expect this to be nearly a perfect bell curve. And it's not. So maybe even I'm surprised sometimes. But again, these are random processes, so I guess you're allowed to be a little bit surprised by the results. And we'll end on this one because that one looks like a pretty good bell curve shape, if I have to say so myself. Anyways, if we randomly select 30 or more individuals, we'd go ahead and say that the distribution appears normal enough for the distribution of the sample mean. We've got one more example problem. I'll try to work through this quickly. This is just a random number generator on our computer, so we're not being fancy about this. We're just saying a basic random number generator, one that uses the uniform distribution, which is, again, what I want you to notice about this is that it's non-normal. With the parameters lower bound 0 and upper bound 1 to generate random numbers. If you generate 10 random numbers, what is the distribution of the sample mean? Well, it's non-normal for sure. If you generate 100 random numbers, what is the distribution of the sample mean? Of course, it's going to be normal because your sample size is larger than 30. Okay, so what about the mean and the standard deviation, right? Well, it doesn't mean very much to talk about it in this first case where we say it's non-normal. But in our second case, we would say that the mean of my sample mean would be whatever the standard deviation of this uniform distribution is, divided by square root 100, which is 10. What is the formula for the standard deviation of a uniform distribution, though? I might have to pull up previous lecture notes. So the formula for that is a little bit complicated. It's 1/12 of b minus a squared for the variance, 1/12 of b minus a squared. And so for us, b minus a is just 1. 1 minus 0 is 1. So b minus a is 1. So when we use the 1/12 of b minus a squared, that's 1/12 of 1 squared, or the variance here is 1/12. So that means the standard deviation is going to be the square root of 1/12. So we do square root of 1 divided by 12. And that's 0.289. So for this, for the standard deviation of my sample mean, this is going to be 0.289 divided by square root of 100, which is 0.289 divided by 10, which is going to be 0.0289. Okay, I think I misspoke earlier. This was supposed to be a calculation of the sample standard deviation. The standard deviation of the distribution of the sample mean. The mean of the distribution of the sample mean should be the same as the mean of the underlying distribution, and the mean of the uniform distribution is just halfway in between the lower bound and the upper bound, and so that's going to be 0.5, just like the mean of the underlying distribution is 0.5. Okay, what about this one? Again, this doesn't make sense to ask about the mean and the standard deviation really. In this case of the first bullet, when we do have a normal distribution, we can calculate the mean and the standard deviation. The mean is just the underlying distribution sample mean, which is 20, and the standard deviation of the distribution of the sample mean is just this, the standard deviation of the underlying distribution divided by square root of n, and in our case n is 30, so this is square root 30, and so this is 20 divided by square root 30, and in the calculator, 20 divided by root 30, that is going to be 3.65. All right, so thanks for watching the whole video straight to the end. Hopefully everything was clear and I didn't misspeak or mispronounce too many times. If you have any questions, feel free to send me a Canvas message, and best of luck on the homework.